morning, everyone. Turn off my speaker here. Okay. Sorry, yeah. Okay, I think you should be able to hear me. Okay. So
Yes, sir. Good morning, sir.
good. I think I should. Any of you all enjoy the short video, right? You can see some of the tough problems the AI is trying to solve, right? We're not looking at trying to find your way from TBR to the Thai UC campus. We're not trying to find out what you have for lunch, right? These are the what do you call that difficult problems that the AI is trying to solve, right? This will help us become a better society, give us a better living, among other things. So I will try to continue trying to find the interesting applications of AI to actually keep you all entertained before the lecture starts. So before I start into the lecture, are there any questions from the previous lecture on Wednesday, isn't it? We just completed the one on the multi-layer perceptron, the multi-layered network. Are there any questions or comments? If not, let's get started. So welcome to this new topic on recurrent neural nets. So far, we have looked at the feed-forward type of neural nets. So for this morning, we will start looking at another type of networks, which is the recurrent net. So we are selecting among the different types of recurrent networks. We are picking the Hopfield nets for various reasons, as you'll see later on. Furthermore, if you notice, this will be the second topic just on neural networks. And then later on, in the after this, we'll touch a little bit about the introduction, basic introduction on these convolution neural nets, especially the deep learning models. We'll touch a little bit of that. So it basically underlines the importance of maybe artificial neural networks in modern society. So what do you hope to learn from this particular lecture or topic that we are going into today and maybe later on in the next session? If you can complete today, wonderful. If not, we will complete in the next lecture. I will not rush through because if I rush through, some of you may have difficulty understanding. Actually, I'm quite surprised also because I think during the previous few tutorials, I think some of you still not able to understand some of the fundamental theories behind the neural networks. So in this particular topic, we will be introduced to what we mean by recurrent neural networks, the concepts behind it, what makes it so different from the feed-forward type of networks. So we will then look at one particular example, well-known example of the recurrent neural nets, which is the Hopfield neural net. Now, the Hopfield neural net has two models. It has the discrete model and the continuous model. So we have the discrete Hopfield net as well as the continuous Hopfield net. We will get some of the major differences between the discrete and the continuous Hopfield net. And finally, we will look at some of the examples of the applications in both the discrete as well as the continuous Hopfield net. So there is something we hope to do in this particular topic on recurrent neural nets, especially on the Hopfield neural net. Now, in contrast to supervised learning, unsupervised or self-organized learning does not require an external teacher. So, same thing with what is doing here in in the universities, right, we have also what we call supervised learning. Like now, we are trying to supervise your learning, focusing on certain topics. At the same time, there are also some things that you have to learn on your own. That is your unsupervised learning. So it's not always just supervised, right? And neither is it unsupervised. If it's unsupervised, you might learn the wrong things, not related, in our example, to artificial intelligence. But it's supervised, we supervise it. But again, there are so many things that we can learn, right? So we cannot complete that, right? In the supervised learning. So we also give you room to have a bit of unsupervised learning. The same thing in artificial systems, right? So artificial systems, we have also supervised learning, and there's also have the unsupervised learning for such artificial systems. Now, during the supervised learning or during the training session, the neural network receives a number of different input patterns. I think we have seen that in the supervised feed-forward neural net. Now, during this training session, right, and the supervised session, the network will discover significant features in this pattern. So when you present certain patterns to the neural networks, the network will, on its own, learn some of the important features, and then from there, learn how to classify such input data into the appropriate categories. For example, if you keep presenting apples to the neural network, right, it will learn what does it mean to be an apple. What are the significant features of an apple compared to, say, oranges? So we are supervising the training, the teaching of your neural network to learn apples and oranges. And then from there, the system will learn these features, and then will tell you, this is an apple, this is an orange. On the other hand, the unsupervised learning tends to follow the neurobiological organization of the brain. That means that the unsupervised learning, it tends to follow closely to how our brain is organized. So that is the neurobiological organization of the brain. Multi-layered neural networks, when trained with the backpropagation algorithm in the previous lecture, are used for pattern recognition problems. So they can be used for pattern recognition problems. They've been used quite extensively. I think nowadays, if you look at the prior work literature review, you find that most of the time they talk about the multi-layered perceptron, which is a multi-layered network, and hardly on other things. But of course, in the past, in the most recent few years, we won't only talk about deep learning, basically in particular, either your autoencoder or your convolution neural net. However, to emulate, to copy the human memory's associative characteristics, right? New term here, associative characteristics. What do you mean by that? We will come to that in the next few slides to explain further what you mean by associative characteristics. Now, to emulate the human memory, right? Our memory, associative characteristics. We cannot fall back. We cannot just rely on the, or rather, we cannot even rely on the multi-layer model, right? Because we'll see later on for that. So we need a different type of network, which is your recurrent neural network. So that is one of the motivations why we want to look at recurrent neural network, because the multi-layer network has certain shortcomings, has certain weaknesses. And one of them is actually it cannot emulate the human memory's associative characteristics. So the next part is what do you mean by recurrent neural network? Now, a recurrent neural network has feedback loops. So from its outputs to inputs. So the feedback will come from the output back to the input. Now, it is because of such loops. It is because of the presence of such loops. It has a profound impact, has an important impact, significant impact on the learning capability of the network. Because of the feedback from the outputs to the inputs neurons, we find that has changed the characteristics and make it powerful in certain way, right? Certain way on this learning capability of such recurrent neural nets. Now let's go into a little bit about the recurrent neural networks. Now, consider the following two networks shown down here, the one on the left and one on the right. The network on the left is a simple feed-forward network of the kind we have already met. You can see information flow is from the bottom to the top, one-way traffic, right? On the other hand, the right-hand one, the one on this right-hand side, right, network, has the additional connection from the hidden neuron, from the hidden unit to itself. This applies to the particular neuron at the hidden link. Later on, you see that there's also other types of architecture, other types of ways you can configure your network, and then to actually, you still need recurrent. That means that there are feedback from the outputs to the inputs. But in this example, we only show you the feedback is at the hidden neuron at the hidden layer. So here. Now, continuing. Now, each time a pattern is presented, right, the unit will compute its activation value, just as in the feed-forward network. Because basically, what? Basically, we are still looking at the basic, your basic processing element. This is your neuron, the artificial neuron here. Now, however, its net input now contains a term which reflects the state of the network because due to the feedback, right? So the computation, the calculation is still the same, except that now it has a feedback from itself or from some other source from itself. There's a feedback. So it changes the computation, as you see in the next few slides. So the now contains a term which reflects the state of the network. So reflects the current state of the network, right? The hidden unit activation before the pattern is seen, right? Now, when we now present new patterns, the hidden and the output unit states will be a function of everything the network has seen before, has seen so far, right? Then it will be a combination of the current and the previous state, they've seen before and the current state. So it's because of this feedback loop. So in summary, the network behavior now is based on its history, what has seen before, and so we must think of pattern presentation as it happens in that. So this one, you have to look at the pattern presentation as it happens in that. So it will be a combination of your historical information and the current information when you present the pattern as it happens in real time. So I'm giving you just one, as usual. There are, of course, various types of various definition of your recurrent neural nets. So I present to you one which is actually quite acceptable, right? So a recurrent neural network, or RNN, is a class of artificial neural network where the connections between units form a directed cycle. So this is more technical definition. Now, because of this directed cycle, this creates an internal state of the network which allows it to exhibit dynamic temporal behavior. That means that exhibit time behavior over time series. So unlike the feed-forward neural networks, because these RNNs, the recurrent neural nets, can use the internal memory to process arbitrary sequences of inputs. So again, based on this, because of such directors or connections, it's now able to use its what I call internal memory that is stored or learned from the previous time, right? To now process new information as it comes in, right? So you go to process new information that comes in and tells you what is supposed to be. As you again see, this will become clearer in the next few slides when we actually look at some of the examples of the power, if you like, the power of such recurrent neural nets. So the idea behind RNNs or recurrent neural networks is to make use of the sequential information. So I think if you see that some of these things, some of these concepts here, you can see that it's so similar to some of the things you have learned in your, for example, your digital sequential logic circuits, right, based on time. Now, in a traditional neural network, we assume that all inputs and outputs are independent of each other, right? So we assume that the inputs only, the outputs from the other neurons do not interfere or do not change the current neuron that you're looking at, the inputs of the neuron, right? Because they are assumed independent. But scientists have seen that, analyzed and seen that for many tasks, that's not a good idea. You do not want to have these inputs and outputs isolated or independent of each other. Maybe you want to combine them so that they can also influence what's happening on the other neuron, also influence on the current neuron. Now, why is that so? Why is such a task? Why is this idea bad? Because for some tasks, this will not work very well, as you see here. For example, if you want to predict the next word in a sentence, you better know what are the words that came before it. What are the words? So look at time now, right? You want to predict what the current sentence will be like. You should know what was the sentences before it. What are the words that came until this current time. So you can roughly see the general direction, combine them and give you a better prediction. Now, the recurrent neural networks are called recurrent. Why? They are called recurrent because they perform the same task for every element of the sequence, with the output being dependent on the previous computation. So basically, it says that the outputs of your neuron should be dependent on the previous calculations. In the earlier multi-layer perceptron network, right, you do not worry about what the previous calculations. You only look at it as it flows through, as it propagates through the network itself. It doesn't have doesn't know what's happened before the current time. Now, another way to think about the recurrent neural nets is that they have a memory, right? They memorize, they know, right? They have a memory which captures information about what has been calculated so far. So they know what has been done until this point in time, right? So in the earlier example, in the earlier model, right, we do not have such a memory, right? Do not memorize such things. So it's one of the major differences of your recurrent neural networks. So I think so far it is still sort of conceptual and maybe quite difficult to understand. But please be patient. In the next few slides, I think it will become clearer what we mean by that. Why such things are so different from your previous model that you have studied so far. So in 1983, this physicist is a scientist studying physics called John Hopfield. He published a famous paper with his partner, right, David Tang. Right? So it's always about John Hopfield and not David Tang. But David Tang is the other partner. The two of them published this paper called Neural Networks and Physical Systems with Emergent Collective Computational Abilities. Again, it's quite a mouthful. Actually, for most of you, it may not mean anything, right? So this one is just another title and doesn't mean anything to you. But because of this, right, so I actually had changed the direction, right, of neural networks until at that point in time. Now, along with the rediscovery of backpropagation, right, because of the backpropagation algorithm and the introduction of cheap computing power, right, this has helped to reignite the dormant world of neural networks once again. Now, what do you mean by that? Until that point in time, before 1983, if you remember, because of certain comments, the field of neural network actually has become dominant. For example, the US government has stopped funding because Marvin Minsky has said that the neural networks itself is not so useful. Therefore, as a result, become dormant. So as a result of this paper of this work by John Hopfield, you see that it actually has restarted or reignite the previously dormant world of world of neural networks. Now, what did he do? What did John Hopfield and David Tang did way back in '83? There's so much changed direction of neural networks research and also maybe acceptance because they added the feedback connections. The added feedback connections, until that point in time, the neural network models do not have feedback connections. So the added feedback connections to the network, so what they mean? That means the outputs are fed back into the inputs for that neuron. And show that with these connections, with such feedback connections, the networks, when you build a collection of these neurons, the networks are now capable of interesting behavior, which might not expect of them. In particular, they can hold memories. They can actually remember things. So this is typical. Again, we're trying to compare, show you from the visually the difference between your feed-forward network and your recurrent neural nets. So in this example, this picture here, you can see that there are two inputs here, and then this is a typical feed-forward network architecture, right? So you have an inputs here, and then you connect to the neurons, and then calculate the outputs from these inputs that we have here, based on the they call it the color fits of the common neuron here. Now, if you were to add a feedback loop from the output of this neuron back to itself, that has actually changed a lot. So with such feedbacks now, they are called the recurrent networks. So network consisting of such neurons where the output of the neuron is fed back into the input, they are called recurrent nets. Now the network operates in a very similar way to the feed-forward ones. They're still the same, except that they have this feedback. So you don't have to worry about the actual calculation. It's still the same way you calculate, right? You sum up everything, right, and then you compare against the threshold, and then you output the final value of that. So such networks operate in a very similar way to the feed-forward ones I explained earlier, and the neurons have basically the same function. So the basic function of your neuron do not change; they are still the same. Actually, that's one of the most important things you must remember. When you talk about neural networks, you always fall back on the simple, basic model of your neuron. As you have seen so far, nothing has changed. So now, with that background of the recurrent neural nets, let's now jump into the Hopfield net and look at the discrete model of your Hopfield net as an example of your recurrent neural net. Now, the Hopfield net uses back the same basic neuron, also sometimes known as your McCulloch and Pitts neuron, named after the so-called inventors, McCulloch and Pitts, with a sign activation function as its computing element. So the only major difference for the Hopfield net is that it uses the sign function. As you see later on why it uses a sign function, right? So this is your discrete model of the Hopfield net. It uses a sign activation function. Now, John Hoffield's quest is actually trying to looking at associative memory, logic and inference, recognizing an order or a chess position. Because you need to remember, if you're playing chess, you need to remember what is the current game. Where are all the pieces in your chess, right? And then passing the word with objects and generating appropriate sequences of locomotor muscle commands are all described as computation. So this is what he's trying to do. in this when we actually started playing around with the neural network with feedbacks. Right. So among other things, is also want to recognize smell certain things. That's one. Okay. So again, let us visit the what I call the famous story about this Russian physiologist, Ivan Pavlov, or Pavlov's dog. So during the 1890s, the Russian physiologist Ivan Pavlov was researching salivation in dogs. When do dogs salivate? In response to being fed. What he did was that he inserted a small test tube into the cheek of each dog to measure the saliva when the dogs are fed. So basically, he fed the dogs with some sort of dried food, so powder made from meat. Basically, so what they call it, dog. I think they call it tablets, or dog food, basically, dog biscuits. So now his hypothesis is that he predicted the dogs will salivate in response to the food placed in front of them. He predicted that the dogs would saliva will start to form, right, when the dogs see food in front of them. So here, this is one example of the setup, right, of the setup of how this experiment was done. But he noticed that the dogs will also begin to salivate whenever they heard the footsteps of assistants who are bringing them the food. So this is what I call it. This is a slight modification of the Pavlov's dog's story. You know, the earlier one we talked about, I think I talked about the using the bell, the sound, to actually in combination with the food, so that whenever you feed the dog, you ring a bell. So in this case, this one that's I think maybe we actually it's a deviation, a slight deviation from the previous story. So in this case, he noticed that the dogs will begin to salivate whenever they hear the footsteps of the assistant who was bringing them the food. So that when you bring the food to the dog, suppose the dogs are in a certain location in the building, so the food has to be brought to the dogs. So when the dogs hear the footsteps, the dogs will start to salivate, even though the assistant may or may not be bringing them the food. Doesn't matter, but the dogs will still salivate. So now, so we have here. Now, before conditioning, right? You have food, you will salivate. Then the sound, or in this case, I call it the bell. And then the just the bell alone initially before the conditioning. Just the sound. And then, of course, there's no response, there's no salivation of the dog. Now, when the dog is trained, when the dog is well trained during the conditioning, right? You have the sound, and then of course the food, and then the dog will salivate. Right? Just the food. The two things are separated. So you have food, the dog of course will salivate, but just the bell alone during the early stages, when the dog is not trained, no response to indicate any salivation of the dog. Now, during the training process, you always ring the bell and bring a food. This is what we call the conditioning process. You train your dog to associate. That's the word now comes in. You train the dog to now associate. Whenever I hear the bell ring, that's food. So it's always together. This was the earlier example. And then we talk about the assistant bringing them the food, the sound. Assistant. Suppose that the assistant will walk quite noisily. So the dog will also salivate. So after conditioning, what he did was that he now removed the food. He only ring the bell, and what you have is you find that the dog will still salivate even though there's no food being presented to them. So this is part of the association we're talking about. This is what we call association. You associate food with the sound of the bell, for example, right? So I think you can also see that for those of you who have dogs, you know that they also can associate certain people bringing them food they can also associate certain time of the day. They know that certain time of the day they will have the food. So of course, this is I think outside the scope of this course, but I've seen reports that says that dogs are very, what they call that, disciplined, not disciplined. They're actually time dependent, not time dependent. They actually can follow the time. They know the time. At this point in time, they expect dinner. At this point in time, they expect their breakfast, for example. So they're actually very they stick to a certain time of day. They know. Right? So this is one. So as a result of that study by Pablo, right? So the conclusion is that the human memory or the memory is based on associations. Now, again, I think if you can, maybe I can bring you to that example, another example, right? I think, for example, maybe certain type of food, certain type of smell of the food brings you certain memories of certain things. For example, the mother's cooking, for example, or something like that. So it is association. That's why we see the power of music is so strong. And I think I saw one report yesterday, not report, it was a radio program that this guy, this radio DJ says that, this song brings back certain good memories to this person. So that's why this person wanted this song to be played, because this song reminded of his, for example, long lost departed wife or husband, right? So together when during the good times, husband and wife are together, they have such a good time, and then they have they play this song. So as a result, they have a good memory of the song. So again, it's this kind of association to certain sound or certain things. May not be just sound alone. So it can be even, like I said, can also be the aroma, the smell of certain food. For that. So now let's talk about association. Talk about associative memory. What is it? What do you mean by associative memory? Now, human memory is essentially associative or association. One thing may remind us of another, and that of another, and so on. So that's why for those of you who actually have been studying this in terms of how do you improve your memory, right? We find that this is one of the ways, right? So you associate. I think I was told that if you want to remember long series of numbers, right? Not 1, 2, 3, 4, something quite difficult to remember, right? So what you do that you maybe tell a story. You associate number 1 with something else, and then number 2 is something, number 5 is something. So as a result, that's how make it easier for us to remember. Because of this, it's actually working on this fact, leveraging on this fact that our memory is essentially associative. So if you want to increase it, improve it, thereby you need to associate certain things with certain other things. So we also use a chain of mental associations to recover a lost memory. I think one of the example I can think of is if you lost you don't know where you put the umbrella after using it. So you will try to remember the last time you saw the umbrella. It was on a certain day, on a certain time, it was raining. What were you doing there? So we try to this how we recover the lost memory. Here, so it's all here. If we forgot where we left an umbrella, we try to recall where we last had it, what we were doing, and who we were talking to. So these are some examples of how we can recover. So based on this, if you look at it, if you think of the whole thing as your one piece of memory, and these are the parts of that memory, so that if you can get enough sufficient parts of it, you can hopefully recover that little part that is lost, which is where you place your umbrella. So we attempt to establish a chain of associations which is associated with the lost umbrella, right? Where we last had it, where we were having it in our hands, right? And then what were we doing at the time, and who were we talking to, right? Was it, or remember the day of that thing, things like that, and thereby to recover your lost memory. That is, where did I place my umbrella? So from that, let's look at the major components of memory now. We try to study now what are the major components of memory. So the components of memory consists of three major parts. The first part is entry, whereby a memory is told to record a certain piece of information. Therefore, you enter information into that, if you like, place or slot of memory where you hold that memory itself. Preservation now. You need to be able to preserve, to hold the information intact, not lost. It cannot be corrupted. It cannot be missing parts of it. So we want to preserve the whole piece of information at that memory location. And recall, of course, is when you want to retrieve it now, when the memory now delivers the information on time or on demand. So basically, what you're trying to do here is that you try to retrieve back where is that where do you think I placed the umbrella, from that memory itself. Because we have entered it and we are able to hopefully preserve it and then try to recall, get that information of where we had that umbrella. So then this leads us to the concept of content addressable memories, or CAM, content addressable memories. Now, content addressable memories also goes by other names. Of course, the other name is also known as associative memories, right? Based on content. Based on the content, you address the memories where you want to find the information. In some other papers, some other books, also known as catalog memories, and of course, the last one is data address memories. So if you look at it, this one, the last one, may make you think of your random access memories in your digital logic circuits, or even your computer systems paper lectures on that. So these all four of them basically describes or maybe describe your content or associative memories. So we are now basically looking at building the foundation of these associative memories. So now look at some of the terminologies. You have the test patterns. So in the next few slides, we talk about test patterns, we talk about output patterns, we talk about content addressable memories, we talk about reference patterns. So what do they mean? We talk about test patterns, we talk about reference patterns, and we talk about output patterns. So this one is basically a picture or representation of your what each of these are supposed to mean. Test patterns, your reference patterns, and your output patterns. Your test patterns, as the name suggests, is after you have actually, I think we go back here, right? So we have entry. So what we assume now is that we have actually stored the patterns, which is your entry patterns, which is also known as reference patterns. Now, after you stored the patterns and preserve the patterns there, enter the patterns there, we want to test it, want to recall, right? Recall, right? Show it certain test patterns. And then from there, we'll give you the answer, which is the output pattern. So basically, this is a simple way of describing or explaining what you mean by test patterns, what you mean by reference patterns, and what you mean by output patterns with reference to associative memories or content addressable memories. Now, let's look at some of the main important characteristics of your content addressable memories. Now, if the initial test pattern is similar enough, over here, if the initial test pattern is similar enough to one of the stored patterns over here, then it will then converge to this reference pattern. It will converge, meaning that if this test pattern is similar to the stored patterns here, which is your reference patterns, right? Similar enough to that, this output will then be your reference patterns, provided this pattern here is quite similar to these reference patterns. So that's why you then can recover this test pattern, then it will tell you that this test pattern is equal to this. As you'll see, I think it will become clearer in the next few slides when we actually try to look at a few examples of such associative memories. So now the beauty of that is what? The beauty of that is that such content addressable memory systems can recognize slightly distorted or incomplete input patterns. Right? If I show you part of a picture, right, and you can tell me that it's a picture of an apple or an orange, even though I do not show you the full picture of an apple, only show you parts of it, right? But the question, of course, is the key thing is, of course, it is only slightly incomplete. Of course, if I show you only 1%, as a very drastic example of the apple, it is highly unlikely you can tell me this is a picture of an apple, right? The same thing as well. If it's slightly distorted, the picture of an apple is distorted, right? Maybe in some way, right? But you can still tell me that this is an apple, right? But of course, the key thing is what? There's only slight distortion. At some point, if the distortion is too much, you will not be able to give me the correct answer, right? So this is the one of the major important points about such content addressable memories, which it can recover and give you the full picture due to slight distortion or slightly incomplete. Now let's look at the concept visually in this picture here. Right, in this picture here, let me look at it. So let's look at the example here. Okay, so basically the concept is what? The concept is very simple. If your now these circles here, what are basically your stored or reference patterns? Then if your test pattern is somewhere nearby here inside this area here, right? It will then be attracted. These are your bases attracted. It will be attracted to converge at that stored pattern over here. Assuming that your pattern actually is slightly is close by or slightly distorted, slightly incomplete, somewhere here. But of course, if the distortion is too much far away, right? Of course, you will not converge to this. It will converge to probably something else. Give you a wrong answer. That is the basic concept, basic idea behind your associative memories. Right? Let me repeat. So these are if you're able to store certain patterns, so this will then form the major attractors. But when you actually want to when you introduce a new pattern or something new, right? Either incomplete or slightly distorted. So the keyword is slightly, so it is somewhere nearby. It will then converge to these individual patterns where the thing is stored. But of course, if your pattern is not slightly distorted or not slightly incomplete, is a lot incomplete, a lot distorted somewhere here, it will not be able to find its way to this correct answer over here, right? And the way the test pattern actually converges is known as your trajectories, how it actually converges to this. I think we will see that later on in the later what I call the example. The dynamics, let's look at the dynamics of brain computation. This is still based on your content addressable memories. Right. The core question is, this dynamics, to understand the dynamics of brain computation is, how is one to understand the incredible effectiveness of the brain in tasks such as recognizing a particular place in a complex scene? So the key question at that point in time was to understand how the amazing thing about our brain, able to recognize a certain particular face in a complex scene, whereby the face itself can be either slightly incomplete, meaning that or slightly changed, right? Or slightly distorted, changed, or incomplete, hidden by a wall, hidden by something else, right? especially nowadays. For those of you maybe who have not been able to get a haircut, right? Things like that. So your actual appearance will have changed, right? Of course, if your hair, if the length of your hair is has changed, but of course it's not totally. It's only, I would say, slightly changed, in the sense that your hair is actually one small part maybe of your face, right? So it's a slight distortion, but you still recognize it. Your friends will still recognize you based on that. Now let's look at the. Oh, maybe I will stop here. I'll stop here, and then continue after this. We'll take a short break, and then we look at how the social nets can be used as a content addressable learning. So we start, take a quick break here, and then we come back 5 minutes time. Now, as usual, before I stop here, are there any questions or comments? Okay, no, I'll stop here, and then we will come back in 5 minutes time. Okay, let us continue. Now let's look at the Hopfield nets, the discrete, in particular the discrete model as a content addressable memory. How can be used as a content addressable memory? So far we look at what we mean by content addressable memory and how the content addressable memories work. What are the concepts behind it? So now one of the what we call the configuration or architecture of a Hopfield net is that as shown here. So actually you can see here we actually have 8 of them, 8 neurons as depicted by these circles here. So these are still the same colored and fixed neurons. They perform the same function as before. Now notice that here is a very simple architecture. Only thing is that the output of each neuron is actually flat back. If we trace back here, it's actually connected to all the other neurons except itself. There are no self feedbacks when you want to use your Hopfield net in the discrete model as a content addressable memory. Look at the second one here. So this is connected. There's a weight here, connected or connection here. All the way back, we trace it back here. But it's connected to the other neuron except itself. So this circle means that it's not connected. So to highlight to you that there are no connections here. So there is connected to everyone else except itself. So basically it means there are no self feedbacks. Now what are the special features? What are the special features of this Hopfield net, the discrete Hopfield net? As I said, as you've seen earlier on in the previous slide, there are no self feedbacks. Now the neuron type, it can be unipolar or bipolar. And the mode of operations, it can either operate in the sequence mode or the synchronous mode. And then the other thing is that it uses the hard limiting function. Basically, the output can only lie between 0 and 1. Now, so let us see how we can develop such a network to learn to memorize this pattern here. Example. So if you have this pattern as represented by this matrix, consisting of four squares in the x direction, horizontal direction, and 5 squares in the vertical direction. So if you were to stretch it out, you end up with 20 neurons. So you can see here, we actually are able to stretch it out. That is how we actually model Hopfield net to actually learn this pattern. Now, let us now try to visualize how to visualize how this content addressable Hopfield net will work. So this will be the current time. This is the future time. So now, if we have this pattern number 9, right, we want to store it and try to retrieve it from the Hopfield net. So you can see here, if you were to present this pattern, then the output will give back the answer, which is the same pattern as before. So assuming that you have actually the network has learned this, has stored this pattern in its memory. Now let's look at another example. Now we have this example of a 9, which is slightly incomplete, or we call it slightly corrupted. What happens is actually slightly corrupted with a few edges missing, and the edges here missing. But for humans, it can still look a bit like number 9. And so we will probably say this is number 9. So let's see what happens if we were to present this pattern to the train Hopfield net and see what answer does it give. Now you can see that after maybe 4 iterations, it actually able to repair back right? And if you like, if you pair back and give you back the answer. That is here. This should be number 9. It's quite similar to number 9 that we have learned in the stored in the memory. Now another example is let's say now we want to show this, present this number 2 to the same network. Right? Let's see what answer does it give this time. Right? So this one actually, because we look at it, the number 2 is similar to the number 3 that is learned before for this network. So in this network itself, it has learned certain patterns, some numbers. So in this case, the number 2 is similar to the number 3 that is learned. So therefore, it's not able to give you the correct answer, give you a different answer. It converges to a different answer, which is the number 3. Right? So this is an example of the associative memory, whereby it can also do error correction, right? Corrected the errors here. And of course, if there's no errors, it can give you back the same answer. Of course, the third case, which is if the pattern itself is not similar, it's not similar to any of the patterns it has in its memory, it will give you a wrong answer. Now let's look at some of the system equations of such a Hopfield net, of such a discrete Hopfield net. Now, the weights in this Hopfield net is not, you do not need to adjust it. If there's no training involved to adjust it. So the weights of this network, the Hopfield net, is actually can be just calculated based on the patterns you want it to learn. So it's unlike the FIFO net where you actually train it. So the training case is very simple. Just one pass, which is you learn, the weights are set according to the patterns you want to learn. So let's look at it. So the interconnection weights, as shown before, right? Without any what they call it, self-feedback. So therefore, it is no self-feedback. So the weight of the neuron I to itself is equal to 0. Otherwise, it is a summation of all the input patterns with the other, and also the outputs of the other neurons, which is the other case. So it's actually itself against the rest. So we sum up everything. So this is the interconnection weights of that neuron. Now, once you set the weights, then what do you do next? For you to do this, what you do, you initialize with your new pattern, with your test pattern. You want it to test, when you want it to show your answer, right? So initialize with your new or unknown pattern. That is, you initialize it like this. You present it and show it to the network itself. Then you update the network until it converges to answer whether right or wrong. So based on this equation here, so the new pattern at time t+1 equals to the summation of the weights multiplied by the inputs. But the weights are formed before, then we have this new pattern. So here, or here. You then multiply by the weights, which is from here. Then you apply, remember, your basic neuron, or your basic McCulloch and Pitts neuron. There's two parts. First part is, of course, your summation. You sum up the weighted inputs, and then you apply your hard limiter, which is here. This hard limiter to the output, to the answer here, the summation. And that will be your new value for that particular neuron. Right? And then, of course, this one tells you the hard limiter of that function here, that is equals to 1 if theta is more than 1, it's positive. Otherwise, if it's 0, it will be, or otherwise it will be 0 or off. This example. Now, this kind of learning, where you actually force the weights to be the summation of these input patterns, is called, also known as your Hebbian learning. Remember, this one actually, if you remember the history of neural networks, this is actually named after one of the investigators or scientists involved in neural networks, which is Donald Hebb. Right? So This is named after him, Fabian Learning. Now, furthermore, from this network, we can also calculate what we call the network's energy equation. So in this case, we don't really need to use this too much. But you find that this one is actually useful in the other model, which we'll cover later on in this lecture on this topic, which is the continuous model, whereby we make use of this energy of the network itself. So the network's energy equation is actually just a summation of the weights multiplied by input patterns. So these are all the states of the input coming and j. So we take all the values of the various combinations of your input states of your neuron and then multiply by the weights associated with the respective interconnection between the neurons. So let's look at another example of the HockeyNet as a content addressable memory here. So in this particular network we are trying to build, we're trying to let it learn, store 8 patterns only, not that many patterns. In this example, we will use a network consisting of 120 nodes, and we will do a synchronous update. And of course, we will still fall back, we still apply back your limiting function. So this is the first pattern we wanted to learn to store, right? Because of 120 nodes, therefore, we actually, because the pattern itself has to be formed within this array or matrix itself. As you can see here, this will be 6, 8, 10, 10 by 12, right? 10 by 12, because 120. So the horizontally there will be not horizontally, there will be 10 columns and 12 rows, right? To actually for us the network to learn, and then we will have a pattern formed within this particular matrix of 10 by 12. So this is how your number 0 looks like. Another pattern is basically your number 1, and number 2. Notice number 2 is slightly shifted to the left. But it's again up to you. We want to do this way. Number 3 actually is over here, and this is how the number 3 looks like. So far we have 4 patterns, right? And then 5th pattern, 6th pattern, the 7th pattern, and the 8th pattern. So that's why we have these 8 patterns. We want the HockeyNet to learn and to see how it performs based on these 8 patterns that we wanted to learn. Okay. Now, once you have learned this pattern, it's very simple, right? As I said before in one of the earlier slides, right? Over here, since you have the patterns, you just add up all the combination of inputs and input states, and that will form the weights of your network. So far as I've learned, I'm learning it through this habit learning. Right now let's say we have this. Now we present this pattern now. I want to find out what can the network tell me based on this pattern. As you can see, I think even for humans, we find it very difficult to tell me what is the answer based on this, because it actually doesn't resemble any of the patterns I've seen so far. It's supposed to remember. So when I present this corrupted or distorted or incomplete pattern, what do you think will happen? So you can see here, maybe you missed it up. So this is the first time we present it, and then at the iteration 0, nothing happens. Iteration 1, I can see certain things happening here, right? Certain squares are filled up. So after about 4 iterations, it actually converges to the number 3 based on this, right? This one actually, I think I cannot show because this is based on basically the MATLAB codes. Okay, Now, basically, the MATLAB codes, again, this is a simulator developed by the author of the book, the reference book by Michael Neminsky, and then using MATLAB. Now, in this example, he wanted to show you what does it mean to if you build a 3-neuron optional net, right? Again, as you may guess, if you have we cannot have any more than 3 because it's very difficult to show it to us how to visualize it if it's more than 3. So in this example, he want to show us, you want to look at the 3-neuron optional net, and these are the patterns you want to store. So this is what? This is 1. So it ranges from -1 to 1. So in this case, this is all. This is -1, -1, and -1. Right. So this is -1, all 3. -1, -1, -1, and this is 1, 1, 1. Right. So you can see here, this is 1, -1. So the top here is -1. Bottom here is -1. Now, based on this simulator, it shows that there are actually 2 stable states. Right, so over here and over here. Now, these stable states are also known as your fundamental memories. As you see why we call it stable and we call it fundamental memories. We can also, in this simulation, we can also show that if you were to randomly generate a pattern, right, some pattern within this space, randomly between -1 and 1, any point here, you find that it will converge to the stable patterns under here or here. That's what is shown in this MATLAB, in this simulator, based on the 3-neuron optional net. It also shows that how the randomly generated states may converge to a stable but undesired state in the center of the space. That means that if you create any point, right, the test pattern, anywhere within this space here, it can also converge to a stable state but not defined, right, undesired, which is actually at the center of the state. What it means is that there's another fundamental stable state here at the center of your cube here, but this is not something you don't want, an undesired state. So this is it shows you the dynamics, shows you how the particular optional net can have exhibit such behavior, right? It can be either a fundamental state or it can be a stable state but undesired state, right? So basically, this is the so this one can basically shows you the initial point where you want to identify the 2 points over here, which is your fundamental memories. Right. So now, this is actually to show you the screen capture of the outputs on the network itself and the space, on the space where the optional net actually works on. You can see here, once I do that, I will find that this is highlighted over here and it's another point over here. Now I want to test it now. I want to test the network on 6 unstable states. So these are actually defined as unstable states. So 6 of them. So the first one is actually what? First one is -1, 1, 1. The second one is 1, -1, 1, 1, 1, -1, and it goes on. So this is actually the 6 states I want to test it against my network itself. So you can see here, the first one is a 1. One of them, I think you don't know which one is that. Which one represents the X, Y, Z, call it, but you can see here. So this one of the 6 states, so one of the 6 possible states, and then they see how it actually reacts when it's presented to this optional net. You can see here, actually it will move in this trajectory. This is the path it will move. It will then converge over here to this particular stable state or fundamental state of 1, 1, 1. Now another one here, I think you might miss it. If you look carefully, We are now looking at the second example, which is over here. This is minus 1, 1, and 1. 1, 1, and 1, that's here. So it's 1 minus 1. So this one is 1 minus 1. Maybe it's not the second one over here. Maybe it's one of these over here. You can see this one here. It's actually so 1 here, and then minus 1, 1. So it's anyway, this is one of the others, one of the 6 states. We want to test it against this network. You can see that again, this state here will still converge back to this point. So you can see this is a very stable and very strong state. That's why they call it fundamental state. It will attract. It will force the patterns over here to converge to this answer 1, 1, 1. Well, actually, why is that so? Because you can actually see here, each of these only differs by one. This is the first three. Differs only by 1 point. So it's quite similar to this particular point over here, right? 1, 1. This is 1, 1, 1. And this third one here, again, I can see here. This is it will still converge. Of course, it doesn't go straight. It goes like this. It gets attracted to something else. But of course, halfway through, they find that this is stronger, so it still come back to this point. So they can see that these 3 points, they are randomly generated, will still converge back to this fundamental state of 1, 1, 1. Now, then the next one is actually over here. It's another state here. One of the now they're talking the fourth state, the fourth randomly generated test case, test pattern over here. Because this is quite far away from this one, so therefore it will converge to this particular state of minus 1, minus 1, minus 1. The next one over here, if you missed it, right? I'll show again. Sorry. Over here, you see that? So this one will. Right, so here it will still converge to this. So this one is similar to this. But of course, this state here is nearer to here, therefore it converges straight to this point here. And the last one is over here, the 6th state. Again, because it's actually, if we compare the differences between this state and this state, and this state and this state. Of course, this one is actually nearer to this one. Therefore, it also converges to this. So therefore, in summary, we can see that of the 6 states that we've seen so far generated, we find that they actually converge to these 2 fundamental or very stable states. So each of these unstable states represent a single error compared to the fundamental. And so when you compare the 6 of these points, compared to the fundamental memories, they only represent a single error. So therefore, they are quite similar to these fundamental memories. So as you have just seen, the fundamental memories attract the unstable states. So these are the so-called unstable states. If we put it here, it will collapse back to this point, either this point or this point. Now we have actually started to look at another one, which is over here, right? So now instead of 1 or minus 1, we have somewhere in a new state in between here, a test pattern in between here. Right? You can see that this pattern here is actually quite close to this one so far. It will pull it towards its orbit. Still within its orbit, so we pull it back to this particular point. So you can see here, this actually in a way reminds us of the gravity pull of this some of these points. So now we will now we actually generate the random. Now we actually want to test it against 3 randomly generated input vectors. This is the first one, right? Represented as a green marker. You see over here. So for those of you attending this lecture through your handphone, you might not see this. So this is one of the points that we wanted to test and see how does it perform against this network. So basically the summary is that all the 6 states here are all unstable. In the earlier example, however, the stable states, also called the fundamental states, are capable of detecting the states that are close to them. So therefore, you can see here, these 6 states are unstable because they will not be there. They will be drawn into. They will be attracted. They will move right, to these stable states or fundamental states. The fundamental memory, the two fundamental memories of 1, 1, 1, and also the -1, -1, right? You will track the first one, the 1, 1, 1, which is a stable fundamental state, will attract the unstable states of -1, 1 and 1, 1, -1 and 1, and finally 1, 1, -1. Now notice that each of these unstable states here represent a single error compared to your fundamental memory of 1, 1, 1. Right? So if you compare this, one, -1, 1, and 1, compared to -1, the other fundamental memory of -1, 1, 1, 1. You find that basically it has 2 points, 2 errors here. That's why it will not be attracted to this the other single the other fundamental memory of -1, -1, -1. Now on the other hand, the other remaining 3 states of -1, -1, and 1, -1, 1, and -1, and finally 1, -1, and -1, they will be attracted to -1, -1, -1, as shown here. So these are the 3 other states will get attracted to this because they differ, they are different from this stable state by just 1 error, whereas they are actually differed by 2 states from this point. That's why we will not get attracted to this point. Right? So it's based on certain mathematical fundamentals. So what is the conclusion here? The conclusion here is that our Hopfield net in this 3-neuron Hopfield net can act as an error correction network. So imagine if these are the errors, for some reason you actually accidentally created an error. So these 3 patterns, these 6 patterns will then be the network will actually correct for you and show you the actual, it will recommend you the actual answer, right? Of these 6 patterns, right? So in a way, it's doing error correction. Now, going back to our earlier statement that we are now creating some randomly generated points within that this space, space of my Hopfield net. You can see that this randomly connected point will actually converge to these stronger stable points. Right? This is the 3rd point, randomly generated, because it's quite close to this, it will get attracted to this point over here. Now, the next step is actually so you can see here the conclusion is that Hopfield net always converges to a stable state. Now, however, this stable state does not necessarily represent a fundamental memory. So this is the next part of our discussion of our lecture. That is, we want to show that other than your fundamental or stable memory, there's also other types of stable memory, but they are not fundamental memory. Fundamental in this case represent the corners of my space. Right? So this stable state does not necessarily represent a fundamental memory. Now, such undesired undesired states are represented as a magenta circle, as we see in the next few slides. So they're no longer green or red, so they are in the magenta color. Look out for them. Now, here we want to now test it. We want to test it with 4 input vectors now. 4 randomly, not randomly. We want to test it against these 4 input vectors and see how they perform against our fundamental memory and also the stable but not fundamental memory, right? So and for these 4 input vectors that we've created now, we want to see how they actually converge to a stable but not desired state in the center of the state space. So these are my 4 new input vectors or test patterns. 1, 0, -1, 0, 1, -1, -1, 0, 1, 0, -1, and 1. You can see here. This is the first one. Over here, you find that this is the first one, somewhere at the side over here. And you see that actually converges to the center point. This is still a stable point. But this stable point is not something you wanted. Right? You only wanted either here or here. So this is still stable, but not fundamental or not what you wanted, or they call it undesired state. Another one is over here. So we have 4, right? It's the second one. So again, this one will get attracted over here. It will not attracted to your fundamental memory over here or here. The third one is over here. You see here, if you have this memory now, it will get attracted. It will be pulled into the center of my square or my cube over here. And finally, the last one over here. It's actually at this part of at this surface here, this side, right? At this wall, it will get pulled to the center. It will not get pulled to either this point or this point. This point is too far away. Of course, it will not get pulled to this point. But this point, yes. The point is stronger than this point, so therefore it gets pulled. Because I think the distance-wise is nearer, therefore it gets pulled to this point at the center of my cube. So what have we learned here? We have learned that, at least we have learned 2 things here, that there's something known as a fixed point attractor. Fixed point attractor, now this is what's a fixed point attractor? Your fixed point attractor is a point of a function that does not change under some transformation. So it's always stable. Right? It's a fixed point, but it can also be undesirable or undesired. Next one is a limited cycle. We have not actually looked at this, but actually this is another type, which is the limit cycle attractor, which is a periodic orbit of a system that's isolated. So basically, it will actually oscillate. And the last one is actually it's a chaotic or strange attractor. So this one has one that is a non-integer or non-negative real number dimension. So this one I think we have not seen it in this example, but the theory has seen that the studies have shown that there are actually 3 types of attractors. These are attractors. This one that over here, one over here, and of course this is similar to this. These are the fundamental fixed attractors. So as a result of this, now what are the major issues? What are the major weaknesses of your HOPU-NET as a content addressable memory? Now, one of them is actually, the first one is actually capacity. Notice that in the earlier case, I think I won't go back. Yeah, I'll go back. The earlier case where we have, you can see that we have 120 neurons that only can store, it was not able to even store 8 patterns. You can see that they're not able to store 8 patterns very well, right? So you can see that so one of the issues is that it's not able to limited. You need to have a very large network in order to store a small number of patterns, right? So there's one first issue is capacity. Now the second issue is that it can get confused. The contents, or it can get confused. What does it mean? It means that if your input pattern is very similar, right, you can get confused. Again, this is something not unnatural, it is natural. Why? Look at our humans. We can also get confused if you look at a pair of twins, 2 persons which are dressed and look almost the same. You can get confused. Or it can be even things like apples and oranges again, right? If the apple and oranges look the same, right, almost the same, you can get confused. So we are not able to remember very well, right? If the patterns are almost the same. Of course, the last part is it can also sometimes, even though the patterns are not similar, it can also give you incorrect results. So these are some of the reported major issues of your HOPU-NET as a content addressable memory. It's not able to remember a lot of things. It can also get confused, and of course, it can also give you wrong results. Now, for those of you interested to know more of this, here I've given you 2 papers. You can actually pick it up, find it, and then to actually look at it. So one of the issues is that we said before, capacity, right? So how do I know what's the size of my network if I want to store, say, 10 patterns? How big should my HOPU-NET be if I want to store only 10 patterns? If I want to store 25 patterns, how big should my network be? So these are some of the people who have just done some studies to actually suggest to you what is the size of the network if you want to store n number of patterns. This one actually is just for your reference. You do not need to worry about this, especially in the exam. Now, I've summarized to you some of the suggested number, how big your network should be. So various papers have suggested the learning capacity of the HOPINET when used as a content addressable memory. Namely, if, this is, I think, everybody optimistic. If you want to store n patterns, means you have n number of neurons. So for example, if you want to store 120 patterns, I should at least have a 120 neuron network. So I think, to me, from what I've seen, this is very optimistic. A more realistic one would be this one. I think the n here will be very pessimistic. I've seen some papers suggesting 15%. If your network should be, if you want to store n patterns, if you want to store n patterns, if you want to store 0.15 patterns, then the network should be n size, n number of neurons. So because you only can store 15% of the size of the network. And then the other more complicated the recommendation is actually n divided by 4 log of base 2n, and the last one is n over 2 log of base 2n. So only basically what this shows is that these three recommendations shows is that only a fraction of the patterns are to remember. No, sorry. This one actually means that if you want everything to remember, only a small fraction, you actually have this size of the network. So you can see here, basically, it also shows you that you need to build a very large system, very large network, in order just to remember a small number of patterns, as shown here. Okay, I think although we've, maybe I'll go a little bit into the continuous model, because it looks like we still have some time left. Now, after the look at the discrete model, now we move on to the mixed model, which is a continuous model. So as I said before, the HOPINET can operate in two models, either the discrete or the continuous model. So you can see here the it's the same architecture, except in this case I did not we did not highlight this in circles. But you can see here again there are no self feedbacks. So when using one application, so basically if you want to use it to solve some of these problems, some of these interesting problems, this is what you need to look at. You need to map your problem into the HOPINET energy equations, as you see later on. So basically, if you want to use it for one example, for this one problem, you can actually you actually map the problem into this equation here. Now, what problem are we looking at? So in this case, we're looking at basically the traveling salesperson problem. Now, why do you have this this complicated looking complex equation? Because we need to constrain, we need to ensure that some things we need to have the output in a certain way, right? So the first part here, we will constrain. We will only ensure that only one neuron will turn on each row. So basically, you can sense that this is the architecture of this will be in terms of rows and columns. So in this case, you can see that with this part of the equation, we will then ensure that only one neuron will turn on each row. Second one here, this part of the equation, right? So it's not so simple as the earlier case, where you just the weights are formed in just one equation. So it's a bit complicated, but it's based on the network's energy equations. Now this part here will ensure that only one neuron will turn on in one column. So this one is one neuron, one row, one neuron in one column, and the next one here is what? A total of only n neurons will turn on. But you still have you can have one neuron in each row, you can have one neuron in each column, but you might not be n neurons. So in this example, in this third part of the equation, we want to ensure that the network itself, when it stabilizes, when it converges, will only give me n neurons in total. right? And the last one here is actually trying to solve your problem with the shortest path. Of all the solutions given to you, you want only the shortest path. So this one will ensure the Hopfield net when operated as a quantitative model will only give me answers with the shortest path. So basically, it's to solve the what you call it, the traveling salesperson problem. Now, how do you then set the weights? The weights are now set a bit different from the earlier example or earlier model. So for this continuous model, we will set the weights as shown here, right? Now, what do each of these means? So here, alphas, all the alpha, there are 4 constants here: alpha 1, alpha 2, alpha 3, and alpha 4. Now, the alphas are set as user. Now, what about this delta function? These are known as your connector delta function. Now, how does what is the connector delta function do? Basically, it is 1. Basically, it checks for either similarity or unsimilar. If P and Q are the same, if you're looking at the similar, basically P equals to Q, then the connector delta function is 1. Otherwise, if they're not equals, P is not equal to Q, it is 0. Let's look at this. So basically, it says that for this example here, for this case, for the first one here, X and Y. If X equals to Y, then your connector delta function for XY will be 1. So if your X and Y are not the same, or I and J not the same, it will be 0. As simple as that. Right? So the connector delta function is very simple. Just check the subscripts. If they are looking at the same value, X equals to Y or Y equals to X, then 1. Otherwise, it will be 0. So now, once you define that, what happens next? You want to now use it. I want to see how it converges, how it moves, how it converges to the answer. So to actually look at the output of the neuron at every iteration, we want to look at these are the equations, right, that actually looks at it. So the equations of motion, actually, these are ones that govern the change in input with time. So basically, it looks at the new input will be the previous input plus a slice of the change in your input itself. Whereby this du by dt is actually equals to the derivation of this energy equation shown here. So this is equal to mu xi divided by tau minus your alpha 1. This is your constant, alpha 1 times your output of that neuron, and then minus the output of another. Now this is xj, this is yi, multiplied by the constant alpha 2, and then the alpha 3 multiplied by the summation of all the total outputs minus n. And is again depend on the problem that you want, how many neurons you want. And then finally, the alpha 4 multiplied by the outputs of the neuron multiplied by the actual problem, which is the distance as suggested by the network itself, right? The connection of X and Y between cities X and Y. Now notice now here, I plus I, the subscript, I plus 1 and I minus 1. This is actually model n. It means that there will be modulus of n. So you will not you will still be constrained within that space, within the space of you're trying to solve a problem, within the space of your network size, right? So the network is n, right? So it will if it exceeds n, it will be go back to the other side. So if it's I plus 1 equals to say 6, if the n is equal to 5, then your I plus 1 equals to 1 equals to 1, right? If it's minus 1, if I minus 1 is actually becomes minus 1, then it will become go the other side, which is n equal to 5. For example, if I'm using n equal to 5. Now this part here, okay, this is you need to initialize it again, initialize to some random initial point. Now this is needed because this is to prevent the system from being trapped in an undesirable equivalent. So this one will actually set for you the initial point. So that's it here. This part here is actually randomly assigned value. And again, how do you randomly assign value? So it must be small. How small? So within the range of plus and minus 0.1 of your initial point. And this is actually to randomize it so they will not always check in the undesirable equilibrium. Output function now. Output function actually is used for your you actually use your sigmoid function now. The first in the discrete model we use the hard limiter, but in the continuous model you will use the sigmoid function. And again, this is a standard sigmoid function as shown down here. Now, one major difference. So in summary, one major difference is between your discrete and your continuous model is that unlike the binary or the discrete version, the weights of the continuous model are not assigned based on the inputs at the start. Right, you can see here, right? So this is actually the weights are not assigned, unlike the are not assigned based on the input patterns, right? But they are actually arbitrarily set. So what can be used for? I think we will. Okay. Okay, I think we will stop here. We'll continue in the next lecture to finish the rest of this topic on the continuous continuous operator net. Okay. Now, before I stop here, any questions or comments? Otherwise, we stop here. Okay. I'll see you back next week. Don't forget, I think for most of you, if you finish your chapter, if you finish your lab number 4, there will not be any more labs for that. I think there's one more group. I think group 1 will still have a lab on, I think, on next Friday. I'm not mistaken. Okay, I'll still be here. The rest of you can leave now. Okay, bye-bye.